Hello again, and welcome to the final part of Unit 7 in Coordination Chemistry. This part is dedicated to isomerism and chirality, and we'll deal with isomerism first, where we look at the different types. The first one that we'll look at is something called linkage isomerism. This is where isomers are formed as a result of different atoms being coordinated to the metal center. And we see this particularly with ambidentate ligands. I refer you back to one of the previous parts of this unit where we looked at the nitrito ligand, where their bonding to the metal center was through either the nitrogen or the oxygen atom. Then we have ionization isomerism, where the ligand and the counterion in one compound can exchange places into and out of the coordination sphere. So let's have a look at the example that's given, where we have the chloride ions inside the coordination sphere here, and the bromide ions are outside of the coordination sphere here. How do we know this? Well, because remember, the square brackets indicate the coordination sphere as such as to how many ligands are attached to the central metal. And in this case, you see that the bromides have now come into the coordination sphere and the chlorides have gone outside of the coordination sphere. We have something called hydrate isomerism now. This is where one of the ligands is water and exchange occurs into and out of the coordination sphere. It's specifically related to complexes where there is water. So let's have a look at the example of chromium 3 trichloride hexahydrate, which you know the formula from first year as this. This can form 3 isomers where we have 6 water molecules on the inside of the coordination sphere. That is still water. If you look carefully at the formula, it's OH2. And we have 3 chloride ions outside of the coordination sphere. And what happens is that this complex, when made, forms a very deep purple or violet complex. Okay. Isomer number 2, what can happen is one of those water molecules goes outside of the coordination sphere. So here we see 5 water molecules, 1 outside, and then one of the chlorides has come inside of the coordination sphere over here. Okay, this results in a pale green complex, which is very different to the violet one. Okay, there's a third possible isomer that can result, where another water molecule can now move outside of the coordination sphere. So we have water, that we have 4 waters, and 1 chloride has now also come inside the coordination sphere, 2 outside, and we end up with a very dark green complex in this instance. Alright, the next example we have is coordination isomerism. This is where we have isomers of different complex ions from the same molecular formula. So in this case, what we see is we have here we have a cation, and here we have an anion. Okay, and these metals can essentially swap places. So in other words, we get rearrangement so that here the amine ligands, the ammonia ligands, were originally bound to cobalt, okay, and the cyano-ligands were originally bound to the chromium. And what happens is that we get a swap taking place, such that now we have the amine bound to the chromium and the cyano-ligands now bound to the cobalt. This is known as coordination isomerism. Then we move on to something which you may know a little bit about. It's geometric isomerism. Here, these isomers are just different combinations of the ligand arrangement around the central metal atom. Okay, so in a sense, you know about cis and trance, and we will go through these in greater detail, but you can see that these examples given on the slide show you cis arrangement. These are next to one another, that's cis arrangement. These are opposite to one another, that is trance arrangement. Here in both cases, that is cis arrangement. This is trance arrangement. Let me just take a different color so you can see what I'm talking about. So that's trance arrangement. And in this case, we also have the cis arrangement here because we have two ligands of similar type. And on this slide section here, you can go through each of the examples and they will explain in terms of what is trans and what is cis. So these two are trans to one another. In this case, A is trans to B, A is trans to C, A is trans to D. And in this case, we have cis to one another, or even this way, these are cis to one another, like this. And then we have trans to one another, okay, where we have that being trans, and if I use the yellow pen, that being trans. So that's how we define cis and trans for various arrangements of ligands around the central metal. Now, the cis and trans geometries often affect reactivity. So if we looked at cisplatin, this is cisplatin, and this one is transplatin. It's a very common cancer chemotherapeutic drug. You'll find that the reaction of the cisplatin with ethylene diamine, this is En, okay, you will find that you will get a reaction with the ethylene diamine ligand. So in other words, the two amine ligands over here and over here are replaced with the ethylene diamine over here, and the chlorides are still cis to one another. However, if we have the transplatin where we have the two chlorides cis to one another and the two amine groups cis to one another, there's no reaction that takes place there. Now, let's look at chirality. Okay. What is chirality? Well, isomers can have chiral isomers, where chirality means not superimposable. It means that they are mirror images of each other. So if we're talking about things that are chiral, it means that we have two possible molecules that are that have a mirror image, and these guys are said to make up something known as an enantiomeric pair. Okay, so optical isomers are optically active, and they can rotate the plane of polarized light in one direction, and the other isomer will rotate the plane of polarized light in the opposite direction. And some examples that you see here, this sort of glass sheet in the center is the mirror, and you can see that this tetrahedral complex here, which I'll label 1, has a mirror image over here, which I will label 2, and those two cannot be superimposed. In other words, you can't lay one on top of the other and get them to fit exactly. That's what means they are enantiomers and they are chiral. Okay. There's another example down the bottom here where we see that these guys are actually cis to one another. So we have this, and here, and here. Okay. And you will see that this also results in us being able to place a mirror plane between them, and they form these two enantiomeric pairs, one enantiomeric pair, which we label as chiral. Okay, if we looked at trigonal, bipyramidal, and square pyramidal complexes, I've already touched on these a bit, where we spoke about Berry pseudo-rotation. So we have, in the top diagram over here, we have the trigonal bipyramid and the square pyramid. You can even see the different point groups. If you've gone over your molecular symmetry, you'll know what I'm talking about. And you will see that the process by which you get this Berry pseudo-rotation is shown over here. To give you a good example is the pentacyanonickelate anion. Here on the left, sorry, on the right, this is the square pyramidal. You can see the square. Here is the square, and there is the pyramid. And this at the bottom is your trigonal bipyramid, and here is the triangle, and you can see the two cyanoligands on either side like that. For octahedral complexes, we also have cis and trans. So you will see, for example, here that these two are cis to one another and these two are trans to one another. Okay, that's simple enough. And now we have another way of viewing octahedral complexes. We have what's called a facial and a meridional isomer. The facial isomer we designate as FAC, F-A-C, and you can see that this here, so if we look at the yellow atoms here and here and here, they form a face of one of the sides of an octahedron, and the meridional will form a triangle through the center. So for example, if we look again at the yellow spheres, we have a triangle here and there. So that cuts through the equatorial. This links the equatorial to the axial. The diagram on the right may help you to see this a little clearer. So this is the Mer isomer and this is the FAC isomer here. Sometimes these FAC and Mer isomers can also be cis and trans to one another. So for example, you can see that if I look at the yellow spheres, this indicates a Mer octahedral isomer, but these black spheres here are cis to one another. And again, this picture on the right hand side here also indicates a Mer isomer, but then in this case the black spheres are trans to one another. So they can be interchanged, and you may be asked in an assessment to discuss all forms of isomers with when given an example. Okay. Some octahedral complexes also show chirality, so you can see very clearly that these, in this diagram here, you have two enantiomers. In this diagram here, you also have two enantiomers, and in this diagram here, you also have two enantiomers where they are mirror images of one another. Then there's one last thing that I need to deal with you, and that is absolute configuration. Now, some of these polydentate ligands that bind more than one position. Okay, if you were to look at this would be the metal center. Okay, and you'd have a connection here and here. And this would be bonded through, for example, if we looked at the ethylene diamine ligand En, you would have two CH2 groups in this position here. Okay, so if this was 3 ethylene diamine molecules, we would have the carbon chain over here and over here. Now, if we looked at the direction of possible rotation of this species, okay, if we were to look at the polarizability of it, we would have the nitrogen going in this direction here, and then this direction here, and this direction here. Now, if I followed this is a clockwise direction that I've just drawn for you, and a clockwise direction based on the definition up the top of the diagram over here says that it is, in terms of absolute configuration, it is a delta configuration. So in this case, we would have the tris ethylene diamine cobalt 3. It would be delta tris ethylene diamine cobalt 3. Now, what happens if the configuration was in the opposite direction? So in other words, we start from here and we go in this direction here. Remember that the cobalt is in the center, and this is a bound point to nitrogens. All nitrogens are bound. Let me just draw them for you so you can see that we're talking about an octahedral complex here, because there are 6 coordination points. I'll draw them here for you as well. And you can then see that the carbon chain is this way and this way. Right, what I've drawn, if you follow the circle, it's an anti-clockwise rotation. This anti-clockwise rotation, in terms of the definition up here, is a gamma. And we see that this is now a gamma cobalt tris ethylene diamine cobalt 3. Okay, the same applies for the oxalato ligand on the bottom of the diagram. You'll be able to see that if I draw it for you, it's going this way, and this way. I've drawn a clockwise rotation, so therefore the isomer is delta, and for this way it's going anti-clockwise. You can see as I'm drawing the arrows for you that I've drawn an anti-clockwise, so therefore it would be a gamma isomer. Guys, this concludes the unit. Please go and do your studying as you would ordinarily do. We have one more unit left, which is catalysis. It's a fairly short unit, and then we will have completed the module. So well done.